Welcome to the talk on the topic of From Non-Negative to General Operator Caste Partitioning. This talk is a part of the Stanford Scholar Initiative. Let's focus on the highlighted words. What do these terms actually mean? Let's quickly find out. Let's roll back to history. Shaky the robot was the first project to address the problem of automatic plan generation. This was in 1970s. In 1995, SAS plus formalism was introduced. SAS stands for Simplified Action Structures. A SAS planning task is represented by the set of all state variables, operators, initial state, and the goal state. An example of a planning task could be like this. An optimal plan minimizes an objective, say minimum power, minimum time, etc. Planning is all about finding the shortest path between the initial and the goal state on the system state graph. 30 binary states result in 2 power 30 states, extremely complex. Studies have shown that constraining the system results in polynomial time planning. However, constrained systems cannot model real-world complexities. This is where heuristics come into play. The A-star algorithm provides a framework under which heuristics can guide the state space search. Domain-independent heuristics is a heavily researched area. Linear programming or LP-based heuristic approach was first introduced in 2007. HSEQ is an LP-based heuristic which uses Petri net state equations to generate the constraints. The author of the HSEQ paper claimed that HSEQ did not apparently belong to any known classes of heuristics. This paper provides a fresh perspective on this. This paper introduces a new class of highly performant heuristics.
Ensemble of heuristics are known to perform better. Partitioning the castes among them is the key. Here is an example of caste partitioning. There are so many ways to partition the castes. How are they different? Caste partitioning directly affects the final additive caste. Optimal caste partitioning offers the maximum additive final caste. This paper explores the perspective of looking at LP-based heuristics as an optimal caste partitioning problem. It introduces potential heuristics, a new class of highly performant heuristic functions inspired by this viewpoint. A typical LP-based formulation based on operator count constraints looks like this. Can we partition the constraints of this LP to create sub-LPs that are additive? If so, what is the relationship between the original LP and the sub-LPs? Shown here is a sample LP partition. The three constraints in LP original have been partitioned between LP1 and LP2. The operator costs have been partitioned for additiveness. The paper observes that the LP original yields the same optimum as the sum of LP1 and LP2 if and only if the operator costs are optimally partitioned between LP1 and LP2. The paper generalizes this for any number of partitions. One of the consequences of the contribution number 1 is that the optimal caste partitions can involve negative caste too. This is a new finding because till now only positive castes were considered. The paper refers to the new scheme as general caste partitioning. The proof details are in a separate technical report. Essentially, the LP duals of each partition are summed up and compared with the original dual to arrive at the conclusion. HSEQ is an LP-based heuristic that derives its constraints from the Petri net state equation. This paper offers a fresh take on it. Since HSEQ is an LP-based formulation, it can be divided into sub-LPs. An arbitrary partitioning scheme cannot yield a meaningful inference. So let us partition by grouping all constraints belonging to a state variable. Shown here is the HSEQ formulation whose constraints are grouped among the state variables S1, S2 and S3. We have already seen that an LP heuristic can be seen as optimal caste partitioning problem among the chosen subgroups. So what do these chosen subgroups represent? It so happens that the sub-LPs are the atomic abstraction heuristics over projection to the state variables. So HSEQ can be seen as an optimal caste partitioning among atomic abstraction heuristics over projection to state variables. Here is an example of an atomic projection over variable S1. Many states in the original state space are merged into a single abstracted state. The authors introduce a new class of heuristics called potential heuristics. Each fact, that is a pair of state variable and its value, is assigned a value called potential. The heuristic at any given state is the sum of all potentials of all facts of that state. The potential difference between any two connected states is directly related to the operator caste between them. Thus, an LP can be solved to obtain the potential value for each fact. The heuristic evaluation is simple addition of fact potentials and involves no LP. Experiments have revealed 10x performance gains for some tasks. We have seen how LP-based heuristics can be seen as an optimal cost partitioning problem. We have also seen that cost partitioning can allow for negative cost too. A new class of heuristics called potential heuristics with superior performance has been introduced. Thank you for listening to this talk. We hope you enjoyed it. We would like to thank the Stanford Scholar Initiative for providing us this opportunity.